Linux application programming, session 14, synchronization with semaphores. If you have any knowledge on any RDBMS, we know something known as locks, table locks, row level locking. We have concept of locking, basically which block the resources conditionally for a specific user. What about these memory areas or variables or data when it comes to operating system? How can we have blocking or concurrency control in the operating system? You can think of that semaphores as that locking system. So introduction to GNULinux semaphores, binary and counting semaphores, creating and configuring semaphores, acquiring and releasing semaphores. Now you can read this as a lock, acquiring and releasing locks. You see, understand that. Acquiring and releasing semaphores, single semaphores or semaphore arrays. The ipcs and ipcrm utilities for semaphores. This is the agenda of the session. In this session, we'll explore the topic of semaphores. GNULinux provides both binary and counting semaphores using same POSIX compliant API function set. You will find similarity now from the previous topic also. Okay, you will find the topic is more or less similar to what we have already learned, because the API, the calls, the syntax, prototypes, you will find similarity. We will also investigate semaphores in GNULinux and their similarities with some other IPC mechanisms. So what is a semaphore? Nothing more than a protected variable. Protected means conditionally protected, giving limited rights to other based on how you have configured it. So semaphore is a protected variable, you can say that. It provides a means to restrict access to resources, to a resource that is shared amongst processes. That's precisely what we know the concept of locking in database is. So it provides means to restrict access to a resource that is shared amongst processes. Two operations are permitted: acquire a semaphore and release a semaphore. So acquiring and releasing, these are the two operations which are permitted on semaphores. The acquire allows a process to take the semaphore, and if it has already been acquired, then the process blocks until it is available. If a process has a semaphore, it can release it, which allow other processes to acquire it. That's the definition. So the process of releasing a semaphore automatically wakes up the next process awaiting for the semaphore on the acquire operation. So you can see that it is a protected variable or a kind of lock, named lock, which is acquired by a process, which can be used by other processes to protect the data. Let's understand a binary semaphore with two. One second. Okay, let's understand a binary semaphore with two processes. In the figure, which I'll demonstrate with the animation, there are two processes which are both are competing for a single semaphore. So we have process A, a binary semaphore, and process B, and this is the execution time passing. Process A performs the acquire first, and therefore it is provided with the semaphore. So process A starts request for a semaphore, acquire it, and therefore it is provided with the semaphore. We are talking about a single binary semaphore. The process in which the semaphore is owned by the process is called critical section. The period in which the semaphore is owned by a process is called critical section. So this process A intend to release it at this point as the time is passing. Now during this process, during this period, assuming that this is the period, during this period, if process B try to acquire the same semaphore, then what will happen? While process A is in critical section, process B attempts to acquire the semaphore. As it has already been acquired by A, so process B is placed onto the blocked state. So process B will be blocked. This is a request from process B for acquiring that. Process B is blocked. When process A releases, it is granted to process B, which is allowed to enter its critical section. So now the process A has released the semaphore, and process B will now acquire it and will be allowed to enter into the critical section. So this now process B has acquired it and it has entered into the critical section, and after some time process B also will release it. Process B at a later time release the semaphore, making it available for acquisition by any other process. So this is an example use case of a binary semaphore, how it works. A binary semaphore with two processes, that's what we have learned. Semaphores commonly represent a point of synchronization in a system. For example, a semaphore could represent access to a shared resource. This ensures that only one process will have the access to the shared resource at a time, therefore providing coordination between two or more users of the same resource. And that's precisely what we know in database, the concept of locking. Think of this as two parallel trains. We have two parallel tracks. This is one train, and train is coming on this track. There is another track, and there is another track here. So and then we have another track here also, and another track here. But now there is one section where we have a single track. Now trains are coming. What will happen? If this train is using this section, then all these others should be blocked. So this is a kind of same thing. Think of parallel train tracks that for a short duration merge into a single track. The single track is shared resource, that is also the critical section. So that's the definition of a semaphore, and that's how the semaphore works. So as two tracks merging into a single track, and then that using the single track for a given period of time, how to avoid that conflict between two processes is basically how you understand the semaphores are, and to understand the concept of semaphore. That was demonstrated with animation also, and this example also explained the same concept. Types of semaphores. We have binary semaphores. The previous example I explained, that was binary semaphores. It represents a single resource. When one process has acquired it, others are blocked until it is released. Then we have counting semaphores. Counting semaphores is like a stack, and we have numbers counted. So we have a limited number of let's say 3 semaphores or 5 semaphores. We define how many semaphores we will have. So first semaphore acquired by this, second semaphore, third semaphore. So how many numbers are left, which one is acquiring what? That is a counting semaphore. It is used to represent shared resources in quantities greater than 1. Consider a pool of buffers. Counting semaphore could represent the entire set of buffers by setting its value to the number of buffers available. So that's a very good example. Suppose we have 10 buffers and we want to specify, we want to control it, how many buffers are available, how many buffers can be used. So we have to make use of them and we have to assign them to specific resources. Therefore, this is a very good example implementation of counting semaphores. Each time a process requires a buffer, it acquires the semaphore, which decrements the value, means number of buffers left for acquisition 9, assuming that we had 10 buffers. Another process requires a buffer assigned, we have available buffers now 8 for acquisition. When the semaphore value reaches 0, the processes are blocked until it becomes non-zero, means it is available again. The way we understood binary semaphores with animation, we'll understand these also with animation to understand how it works. When a semaphore is released, a semaphore value is increased. Obviously 8, I was talking about 9, 8, 7, 6. Now at this point one of the old process released the semaphore. So we have again 8 number of available. One more process released. Now we have 9. Now one process acquired. We have 8. So a process will keep on increasing and decreasing depending on how we are handling and like how the processes are acquiring and releasing it. When the semaphore is released, the semaphore value is increased, therefore permitting other processes to acquire a semaphore and associated buffer. Counting semaphore example. In the example, we have same process. Each process requires 2 resources before being able to perform its desired activities. So this is an assumption that we have 2 resources and both these must be acquired by a process to complete its task, continue its task. The value of the counting semaphore is 3, which means that only one process will be permitted to fully operate at a given time. That's a very good example to understand. Process A acquires its 2 resources first, which means that process B blocks until process A releases at least one of its resource. So same process A, process B, counting semaphores 3 and the timeline. Process A acquire 1 semaphore, process B acquires 1 semaphore, process A acquires another semaphore, so process 1 A has acquired 2 and process B has 1. Now no more available because we had only 3 semaphores. What will happen now? Process B will try to acquire but will not be granted. So process B try to acquire but it is blocked because there are no more semaphores available. So after some time, if process A release one of the semaphores, then process B will be allowed to acquire and therefore now process B have 2 semaphores. After that, process A also release that and now we have one more available, 2 are acquired and process B also released 1 semaphore, so 1 is left and finally it is left. So this is the overall process of counting semaphores, acquiring and releasing semaphores. That makes the concept very clear. Overview of GNU semaphores. Using the Semaphore API requires that the function prototype and symbols be available to the application. Type.h, ipc.h, sem.h, which is semaphore.h header file. So we must enable it. So that's the prerequisite. Therefore, some libraries are to be included. This is done by including 3 header files. So creating a semaphore. Same process, same methodology, quick walkthrough or quick overview. Creating a semaphore. In the example, in the source files, session 14, src, semaphore create .c. Can refer to this. The program is studio.stdio.h, semaphore.h and common.h. We use semget API function, semaphore get API function. It takes the semaphore key, semaphore count and a set of flags. Now you see, you will find it related to the previous topic, similar to that. Semget ID, 1, permissions and the flags. And I'm sure by now you understand this is IPC create or IPC private or what. So these flags, and they are similar to the message queue, similar concept. We'll specify the need for one semaphore. The IPC create flag specify that semaphore is to be created. We also specify the read-write permissions to use. When a semaphore is created, its value is 0. When the application runs, a new globally available semaphore could be available with the key identified by what you have specified here, my semaphore ID. Any process in the system could use this semaphore now. Getting in releasing semaphores. This is a complete example which makes this concept clear. Semaphore operation as semop. The header files, the main program. Let's understand this program. We begin by identify the semaphore identifier with segment at line number 12. Semaphore ID equal to semaphore get, and the semaphore which we created in the previous example, semget my semaphore ID, alright, and 1 and 0. What this signifies we already know because we have been using this value. If it is successful, we build our semaphore operation structure. Since we have only one semaphore, we'll use the semaphore number 0 to identify it. To acquire the semaphore, we specify an operation of -1. This subtract 1 from the semaphore, but only if it is greater than 0 to begin with. Getting and releasing the semaphore, same program continued. With our sem buffer created, that is a variable SB, structure semaphore buffers SP. We created, we use this with our API function semaphore operation, the semop, and we specify the semaphore ID and the address of the buffer. So we verify that what it returns. If it is equal to -1, then we are saying that it is semaphore operation failed. We specify our semaphore identifier, our semaphore structure, and then number of semaphore buffer that we passed in as 1, that we want one semaphore. This implies that we can provide an array of semaphore buffers, which we will investigate later in the same session coming up. As long as the semaphore operation can finish, then it returns with the success. This means that process performing the semaphore operation has acquired the semaphore, has acquired the concept the way I try to explain it, compare it with the log, so has acquired it. Releasing a semaphore, program with the same for this purpose is semrelease.c in your source code file. So semget, verify the operation and release the semaphore, sem released, and this is what we are doing. We are releasing the semaphore. In this example, our semaphore operation element is 1. We are releasing the semaphore, which means that we are making it non-zero and therefore available. Executing the sample semaphore applications. This is the same example what I used in the discussion so far. GCC semaphore create. So we are compiling the program, we are running the program, and you will get the message semaphore created a semaphore and with the identifier 2. Then semaphore acquire, ampersand sign. So we acquired one semaphore, attempting to acquire semaphore 2, we acquired it, and then we release the semaphore. So releasing semaphore 2 released, and semaphore 2 acquired, that is by another program. So that's the simple running of the code discussed so far. So 2-3 function calls and overall concept is that easy to understand. But what is the real application? Without a real application, probably the concept will not be that clear. So first, let's look at the API you discussed so far. Configuring a semaphore first. That is Semaphore, semcrd is the name of the program file, which is discussed here. Semaphore get, semaphore ID is greater than 0. Then we are using like semaphore CTL. Configuring that we are counting and we are using semaphore CTL function for the operation, for the configuring and controlling the semaphore. There are a number of elements that can be configured for a semaphore. Let's look at the reading and writing a value of the semaphore. The semaphore is identified by an index because it could represent an array of semaphores rather than one. The return value is either -1 for error or the count of semaphores. Setting the current semaphore count. We can set this value using semctl API function. In this example, we are setting the semaphore value at line number 6. No, value to 6. Where is the value 6 is being set here? Can you see that? I don't see that value 6. Return value greater than value 6. Okay, that might be coming from the common file, the common.h file, semaphore ID. So definitely that might be coming from the common.h file. Oh, here it is. Sorry, semctl, semaphore ID, set value 6. This is the function which is used in line number 16. Setting the value to 6 changes the binary semaphore to a counting semaphore. 6 semaphores acquires would be permitted before an acquiring process would block. Removing semaphores, we call it with a special function ipcrm ID in line number 14. This is removing the semaphore. Removing a semaphore is also performed through the semctl API function. After retrieving the semaphore identifier, we use this to remove the semaphore using semctl API function and ipcrm command. Now let's understand all the API functions used in the quick walkthrough with their prototypes, return types and the parameters. The Semaphore API handles not only the case of managing a single semaphore, but also group or array of semaphores. So these are the Semaphore API functions and their uses. Semget, create a new semaphore and get an existing semaphore. Semop, acquire or release a semaphore. Semctl, get info about a semaphore, set info about a semaphore or remove a semaphore. These are the three functions in the API which are used to control, manage semaphores. We'll go one by one. Semget API function. Two fundamental roles it plays: creation of new semaphore and identify an existing semaphore. Response from semget is the semaphore identifier. And this is the prototype. Semget key and sems, that means number of semaphores, and the flag. The key specifies system-wide identifier and must be non-zero or IPC private. The IPC private variable tells Semaphore semget that no key is provided and to simply make one up. The developer can create a single or multiple semaphores. We are using semget to get an existing semaphore. This value can simply be 0 if that is the case. Semget API function. The SEM flag, that is Semaphore flag, allows the developer to alter the behavior of the function. It can take three basic forms depending on what is desired by the caller. Create a new semaphore. In this case, the Semaphore flag must be IPC create. Second, creation with constant, that if the semaphore already exists, then error is generated. And third, a 0 for this flag and identify that an existing semaphore is being requested. These are the three possible values of the flag. Three different forms. Assuming semaphore ID is an integer value and my semaphore is of type key underscore t, to create a new semaphore of the private type we can use, now we can make the function very easily, semget IPC private 1 semaphore create and permission 0666. Once the semget call completes, our semaphore identifier is stored in semid. If an error occurred, a -1 would be returned. If semid was somehow lost, there would be no way to find this semaphore again. Let's create a semaphore using system-wide unique key value hexadecimal 222. If the semaphore already exists, we don't simply get its value, instead we fail the call. Now think of the options available and what we are going to use in this function call. So here we are using this value semaphore get. We are passing the identifier semaphore create, ipcxcl and permissions. Now this flag, this is talking about that if this already exists, then fail the call, and we are making a create call with this identifier. So this call is a very good call where we are saying that if semaphore already exists, then don't recreate it because that might be used. Existing semaphore might be in use or should not be deleted. Just fail in that case, and the permissions and all that options. Use of ftok, that is a token, and that stands for file token. To create a unique key value, we'll assume that our file and path are defined as this, which similarly, like that's what we learned in yesterday's lecture also, that if we use the key from a given file in the file system, that will ensure that it's always unique. And here we are using the same. First we are creating the key, exactly same segment. In this slide you will see that is a copy paste of the same slide. My key, file token, file name and semaphore ID. Now we are specifying my file as a token, as a key. Each time file token is called with those parameters, the same key will be generated. As long as each process that needs access to the semaphore knows about the file and the number, the key can be recalculated and then used to identify the semaphore. An array of semaphores. How can we create a group of semaphores, multiple semaphores? Can be created by simply specifying a number of semaphores value greater than 1. So this is what we are saying, nothing else, only that number. We are creating 10 semaphores. The result is a semaphore array being created that consists of 10 semaphores. The return value semaphore ID, sem array ID, represent the entire set of semaphores. In the example, we'll specify our key value and no command. So here we are creating semaphore. This is the ID we are creating, right? Semaphore ID is -1. Semaphore does not exist. Semaphore internal value, like message queues, a set of defaults is provided to the semaphore as it is created. The process can override some of these parameters, and same set of parameters, if you notice carefully, only thing is that this word is changed here. Here it is semaphore. Permission user ID, that is creator user ID, owner user ID, and then creator group ID, owner group ID. Same set of values are there, except that first prefix is changed. Now it is, you will find yes, it is similar to the previous topic, except that some abbreviations and prefixes are changed with the same meaning. semctl API function. It provides a number of control operations on semaphores or arrays. For example, setting the value of a semaphore or removing a semaphore or semaphore array. Semaphore ID, numbers and the command. The second argument specifies the semaphore number of interest. The third command to be applied, and then potentially another argument. Let's look at the setting of semaphore value and then returning its value. In this example, we first set the value of semaphore to 10 and then read it back out using get value. So integer semaphore ID, set the semaphore to 10. So set semaphore CTL value, set value 10, and then read the semaphore value, that is the return value, using semctl, semaphore ID and get value. So this value variable will have 10 now after this call. The getPID command allows us to identify the last process that performed a semaphore operation on the semaphore. So that can be done getPID. We can use getPID here. This will get the PID of the process that performed the semaphore operation. If no semaphore operation has been performed on the semaphore, the return value will be 0. Operations that can be performed using semctl. These are the possible operations: get value, return the semaphore value; set value, set the semaphore value; get PID, PID of the function; get count, number of process awaiting the defined semaphore to increase in the value. It should be integer, that is fourth argument should be integer. Then get ZCNT, number of processes awaiting to define semaphore to become 0. So these are the operations that are allowed to be performed using semctl on given semaphore. The getCNT command. To identify the number of semaphores that are currently awaiting a semaphore to increase in value, we can use the getCNT command. We can also identify the number of processes that are awaiting the semaphore value to become 0 using getZCNT. So this is the example. How many processes are awaiting the semaphore to increase? So we can use this. This will be stored into count after we make this call. GETNCNT. How many processes are awaiting this semaphore to become 0? GetZCNT. So NCNT, ZCNT are the functions, interesting functions, which can be used to identify how many processes are waiting for it to increase or to become 0. A semaphore array of 10 semaphores. The creation of a semaphore array is performed using semget API function. Since we are going to create and remove semaphore array within the same function, we use IPC private key. Or our max semaphores symbolic defines the number of semaphores that we will create, and this is the example semaphore all.c in your source folder, which is discussed here. So we are defining some variables here, hash short array semaphore array size, how many semaphores we are created. This value max semaphore is defined into common.h file. We initialize our semaphore value array. We initialize each semaphore to 1 plus its semaphore number. At line number 32, we get array, argument array is equal to semaphore array. Where are we increasing the semaphore array? We are increasing one by one. Semaphore array I is unsigned integer short, so we are incrementing the value. And because the number of semaphore, the value is stored into this max semaphore, so we are using this max semaphore. At line number 35, we use the semctl API function and set all command to set the semaphore values. On return of this API function, the semaphore array identifies by semaphore ID has the value as defined in semaphore array. So this is semaphore all.c, same program, continued explanation. The get all command is used to retrieve the array of values for the semaphore array. We first set our argument array to a new array at line number 42. That's what we do here. And at line number 45, we are using get all and setting it in this variable. At line number 45, we call semctl again with our sem id 0 for sem number and get all command and our semaphore union where our semaphores will be stored. To fetch what we have read, we loop through the semaphore read array and emit each value for each semaphore index within the semaphore array. This is the complete listing of the same program. So I'll leave it to you for study because we have discussed the functions and the calls and the meaning. Therefore, the complete example walkthrough will help you in understanding the flow. So this is for your reference only. Executing the application. So when we run this application semaphore all, we will get this semaphore 0 value 1, semaphore 1 value 2, and we start. Executing the application produce this following. Not surprising, the get value emits the identical output as that shown in the get all. Reading semaphore information using ipcstat. ipcstat command is used to retrieve the current information about a semaphore or semaphore array. The data is retrieved into a structure called semaphore IDs, semaphore DS, that is semaphore ID data structure, and contains a variety of parameters. This is into semstat.c in your program. Updating fields in semaphores. 3 fields can be updated through another call to semctl using ipcset. They are the effective user ID, that is semaphore permission user ID, and effective group ID and the permissions. If you recollect, exactly same 3 sets of possible values were there in the previous example also in the lecture we discussed yesterday. So we have argument buffer, retrieve the value and then update the value. Semaphore buffer dot sem permission mode 644, earlier it was 666. Updating fields in semaphore. 1 IPC set semctl has completed. The last change time is updated to the current time. Finally, ipcrm id command permits us to remove the semaphore or semaphore array using this snippet code. You can see this. If any process were currently blocked on the semaphore when you are trying to remove it with the RMID, they would be immediately unblocked. With an error returned, the error number would be set to EIDRM. Semop API function. It provides a mean to acquire and release a semaphore or semaphore array. The operation provided by semaphore op are decrement, increment, a semaphore. What was discussed, demonstrated using the animation. Integer semaphore op, integer sem id, structure sem buffer, s ops, and number of operations, ns ops. The sem op takes 3 parameters: sem id, sem buffer structure, and ns ops. The structure defines the semaphore, number of interest, and the operation and a flag. So structure, sem buffer, unsigned short semaphore number, short semaphore operation, and sem flag. Now this is a sample application for the complete use. Our application acquired 10 semaphore in one operation. We build our semaphore buffer array as acquires and also initialize the semaphore number fields with a semaphore number. This specifies that we want to acquire each of the semaphore in the array. If one or more are not available, the operation block until the semaphore are not acquired, until they are acquired. And this is the application. Semaphore acquire, that is semacq.c in your source code file directory. We specify an array of semaphore buffers at line number 9. The Semaphore Operation API at line number 27 acquires the semaphores. As long as the return value is not -1, we have successfully acquired the semaphore array. And we are verifying it. If it is -1, then we are failing it. We are saying that operation is failed. Just verifying it. We could specify -2 for each semaphore operation, which would acquire that 2 counts of the semaphore would be required for successful acquisition. Like in the animation, the count animation example, if you notice, the process required 2 semaphore for successful work. So that can be done here with -2, because -2 means we require minimum 2. The release operation is done with this. We increment the semaphore instead of decrementing it, because that will increase the semaphore count. If you notice, they are just variables. You are incrementing, decrementing it, counting it, and we are acquiring them, and we are just kind of it is actually, you can use it to allow how many processes are allowed, how many processes will be running, and that can count your processes, how many processes you have created already. So how many identifiers, how many files, wherever you need to keep a track on number of operations or blocking or creating a locking in terms of total number of operations allowed, you create these semaphores. We increment the semaphore release instead of decrementing it. The sem flag within the semaphore buffer structure permit us to alter the behavior of the Semaphore Operation API function. The flag options, sembuffer.semFlag, that is sem undo the semaphore operation if the process exists, and no wait, return immediately if the semaphore operation cannot be performed. Wait for 0 operation, the process is blocked until the semaphore value becomes 0. This is performed by setting semop to 0. That's what we can specify. Semop equals 0, sb.semop equals 0. User utilities for this, we have ipcs utility, the way same utility, but this time passing the argument as s for semaphores. Commands remain the same, options are changing. Yesterday we discussed the ipcs command. This presents all the semaphores that are visible to the calling process. Let's create semaphores and get details. So create it, verify it, and you will see the details. Exactly same way. You want more details, you can use -i option, the way we discussed yesterday, -s, -i and 2, and you'll get the details. So this is the same utility we discussed yesterday. We see the details of the semaphore with other information. If you were to perform the release operation and then perform this command again, we would see this kind of output, semaphore release. After releasing it, you will see the releasing semaphore 2. We can also delete semaphores from CLI using ipcrm command. ipcrm -s semaphore ID. It also uses the semaphore identifier to specify the semaphore to be removed. So the summary of the lecture is what? We introduced the Semaphores API and its application of inter-process coordination and synchronization. We begin with a quick tour of the API and then followed with a detailed description of each command, including examples of each. Finally, we reviewed the ipcs and ipcrm command and demonstrated their debugging and semaphore management.